All right. So, hey, everybody. Thanks for making it. Today we have Guillaume from Aztec to present on Noir, which is a new language they've been developing. And so, yeah, thanks so much for joining us. We really appreciate your time. And yeah, take it away.
Okay, yeah, thank you. Thank you also for inviting me, sorry. So yeah, I'm going to talk about Noir. It's really to be, so yeah, my purpose is to show Noir with an example. So like a real life example, no, not a real life, but an example, and I will show code, we'll do some live coding session. So my example is based on sudoku, so it will be very simple. It will be a beginner entry-level talk. But yeah, so before I start, just to give some motivation, I am considering a simple use case. So this use case is, let's say you want to distribute a prize to the first person that is able to solve your sudoku puzzle. So a standard way to do that is to ask users to send their submissions via email. Then you can write a small program to check that the submission is correct, and then you can just send the prize to the first email that you receive that is valid. So I think this works quite well, but it's not completely secure. Like there are some manual process and so on. And like, let's say if the price is very big, if it is a lot of money, maybe you want something that is more secure. So yeah, bottom line, it's not really secure. So what you can do, like, yeah, we can say that we can remove a lot of manual steps by just using a blockchain. So let's see how you would do that in a blockchain. So now you ask your user to send submissions to a smart contract that you write. You can reuse the code of the small program that you wrote to check the submission. So to check it now, you need to check it inside the smart contract. And the smart contract can then send the money to the sender address of the first transaction that is valid. So this solves a lot of problems, but I think it's not secure as well. So like one reason that it's not secure is that because like you are sending your submission to the blockchain, but what that really means is that there is some miners, validators or whatever, that are looking at the transaction pools. And so they can see your solution before it's in the blockchain. And what miner, I think they all do that. They try to do MEV. And in that case, the MEV with your transaction is very easy. They just take your solution and then submit their own transaction instead to get the price. So this is not safe at all. It's not secure. And of course, the solution to make it secure, it's not. We see that the problem is that you provide the solution. So the proper way to do it is not send the solution to the puzzle, but instead you are going to send a proof that you have a valid solution. The smart contract will verify this proof and then will send you the money. Okay. Do you have any question on this small use case? Don't hesitate to stop me if you want to ask a question. Okay, we'll check the chat from time to time. All right. So we need to prove a sudoku solution in zero knowledge, and we are going to use Noir. But first of all, what is zero knowledge? What does it mean? What is a zero knowledge proof? I suppose you all know what it is, so it will be very, very short. So we are going to use zero knowledge proof. That is the proof that the statement is true and it's zero knowledge, meaning that it does not reveal anything else. except of course that the statement is true. So in our case, the statement is simple, is I have a solution to a particular Sudoku puzzle. This is a statement we want to prove. If you don't consider zero knowledge, the normal way to prove that would be to provide the solution, but we have seen that this is not good enough for us. And it is not zero knowledge to provide the solution because it reveals why the statement is true. We just want to say it's true. We don't want to say why it is true. Okay, and is this even possible? So yes, of course it's possible. And for Sudoku, there is I think a neat way to explain this. So one way to prove in zero knowledge that you have a valid solution to a Sudoku puzzle is to use cards. So you can use 9 deck, and each deck has cards from 1 to 9, and then you just lay down your solution on the grid, except that you put your solution face down and face up only for the cells that correspond to the puzzle. So all the gray cell will have the card face up, and all the yellow, is it, or blank, let's say, the blank cells will have the card face down. Okay, so this is just the setup. So the setup is the card decks. Everybody knows. Everybody know what are the cards, and then the provers lay the cards on the grid. Then how we can convince a verifier that we have a valid solution. So this is the proof. So for this, the verifier is selecting, let's say, selects a line, for instance, the first line. Yeah, I've not completed the full grid, but you see my point. So it selects the first line, the prover takes all the cards of the first line, he sorts them from 1 to 9, gives them to the verifier, and the verifier checks that, okay, it's the card from 1 to 9. Then he knows the line is valid, but it doesn't know, because it doesn't know the real ordering of the cards, it doesn't know where are the numbers. And then he can repeat this for all the lines, all the columns, and all the square. And at the end, he will be convinced that this is a valid solution. Okay. So this is what we want to do with Noir, but we are not going to do it with Noir yet. First, we are going to do it in Rust. So it's not going to be zero knowledge, of course. It's just a simple program to check a Sudoku solution. But it's important to understand this program, but it's very, very simple. So I have only 3 functions: the main, and then these 2 functions, check puzzle and check line. So the main is taking a solution as an argument, and then the puzzle. It checks that the solution corresponds to the puzzle, and then it checks that the lines of the solution are valid. Then I don't do the column on the square, because if you know how to do the lines, it will be exactly the same for the columns and the square, so it's not interesting. Okay, so let's see what is check puzzle. So check puzzle. So my solution is represented as let's say the Sudoku grid is represented with a 2D array. So it's an array of 9 lines. On each line is an array of 9 numbers. Okay. For the puzzle, it's the same. So when the cell is blank, the puzzle at this cell, the value is 0. And when it is not blank, it is gray, it will be the number of the cell. Okay. And then to check that a solution corresponds to a puzzle, I just need to check that the gray cell corresponds. So if it is not 0, it must be the same, else I return false. And if all my check pass, then I return true. Is this clear to everyone? Okay, I think it's very simple, so it should be clear. Then to check the line, so I do it for all the lines. here. So I do two things. I check that all the numbers in the line are from 1 to 9, first thing. And the second thing that I do is that I check that there is no duplicate. So I do this with this helper array that I call check. It's initialized to 0 here. And then at the index corresponding to the cell value of the line here, if it is 0, I set it to 1. And if it is not 0, that means it was previously set to 1. So then it's that means it's a duplicate. So I have an error, I return false. And if all my check pass, then all my lines are correct. Okay, again, is it clear for everybody? Okay, good. So now we are going to try to do the same thing, but with Noir. So what is the difference with Noir? So Noir, the purpose of Noir is to be able to use zero knowledge proofs. So you use Noir to define your statement that you want to prove. So a statement is a Noir program. So or maybe it's the reverse. A Noir program is a statement that you want to prove. So you write your program using Noir. And then with Noir, you can compile this program into what we call a circuit. And then you can, Noir can give this circuit to a proving system to generate a proof, a zero knowledge proof, and verify a proof. Okay. So when we design Noir, we have these three goals. This is our our motto: so safety, simplicity, and performance. And to do that, to achieve this, we have implemented a full compiler engine in Noir. I think that a lot of projects are just interpreters. With Noir, we have a full compiler. So how do we achieve, for instance, simplicity? So we do this with the front end of the compiler. So we have a powerful type system that is implemented. And then we can implement like what a developer would expect from any programming language, that is like functions, loops, conditional, but also structs, tuples. We have arrays, and we have also generics. So quite powerful type system. Also, you can organize the code with using modules, using submodules, and even external crates that are on GitHub. You can reference them. So yeah, Noir is our goal, at least, is that it's very, very to use, and then you can organize your code with structs, with modules, etc. So having the code organized like that and having an intuitive syntax, I think it's very important to write safe code. So this is important for safety. Another thing is that we abstract a lot of cryptographic constructs. So this is just example. So we have a standard library where we implement many cryptographic primitives. We also expose an open interface for the proving system. So Noir is not tied to a platform. It's not tied to any proving system. You can change your proving system. And then my last example, yeah. So if you have a Noir program, you can also, with Noir, generate a verifier smart contract that will verify the proof for your program on chain. I mean, you need to, of course, to publish the contract, but you have at least the code of the contract for the verification. So this will be useful for our use case where you will need to verify the sudoku proof inside the smart contract. Okay. So the last point is performance. So yeah, so we have some intermediate representation for the program. This is a low level, and we can do many, let's say, classical compiler optimizations on it. So this is quite powerful. And also we benefit from Aztec expertise because we are the only DSL, so the only language that is using Aztec proving system. And I suppose, I don't know, but I think that it is the fastest currently in production proving systems, the one from Aztec. And also we can use custom gates like that are implemented in the proving system of Aztec. So this also this is very powerful, and I think we are like probably the only language that allows to do this currently. All right. Of course, big disclaimer, this is work in progress. So this is what we want to do. We are not there yet. We want to be intuitive, but we will find sometimes that Noir is cumbersome. We want to be safe, but yeah, we have bugs, so it's probably not safe. But the good point is that we are working on it, so it will improve over time. So if you write a Noir program now, it will just get better by doing nothing, just by upgrading your Noir version. Okay, so now we are going to do coding with Noir. So I think I told you, but Noir is similar to Rust. That's why I was showing Rust before. So the syntax on Noir is quite inspired by Rust. So what I'm going to do is I'm going to take the program we wrote in Rust and use it as is and try to make it work with Noir. So there are a few things to consider. So like for the zero knowledge part. So the statement we want to prove is that we have a solution corresponding to a puzzle, and then the solution is valid. This is a statement. And what is zero knowledge? So what we don't reveal is the input to the main function. So main is the entry point in Noir. So this is a statement we want to prove. It is the program that is it is the main function, basically, what you are going to prove. And to give the input to the main function, you need to have this prover toml file with the values. Okay, so it will be used by the prover to generate the proof. You see here, that was not in the Rust program, but you see here a pub. So this keyword is because sometimes you want to have some inputs that are not private but public. This can be interesting. In our case, we want to people to know what the puzzle is. Another solution will be to hardcode the puzzle in the program, but that would be not easy to check what is the real puzzle, because when we compile into a circuit, it will not be readable anymore. So it's better to use it as an argument, and then you just say pub, and then it will be a public input. So when you generate your proof, it will also generate a verifier toml file that contains all the public input for the verifier. Okay. So what I'm going to do is going to through all the errors that you will get if you try to do it yourself. So we'll do it. We will see plenty of errors. So I will show you how to solve these errors, how to work around what I think is the biggest blocker right now, and we will also try to optimize the program, which means reducing the gate count. So gate refer to the gate of the circuit that is generated from your program. Okay, so to do that, I'm going to use, oops. Okay, so here I have the program. This is a Rust program. I have my prover toml file with the values. So I can just try to execute it. So let's generate a proof. So obviously it doesn't work. So we'll see all the errors we get. So the first error is string are not implemented. So this is something we want to implement, but for now we don't have string type in the language. This is not really important because we just use here the string to print something, but printing something and generating a proof that you print something doesn't really make sense. So anyway, we will not support print statements. Or yeah, maybe we will probably support it, but just for debugging purposes. Okay, so it will not be really inside the circuit. So yeah, so what I'm going to do, since I cannot print, what I'm going to do is to return a value. Yeah, I return a Boolean instead of printing something. So I already have the Boolean here. So like that. Okay, so I need to remove here the prints. Okay, so far so good. So now let me try again. Oops, much more errors now. So first error, Noir has no logical operators. So yeah, again, this is something that maybe will change in the future. So the reason we don't have it, oops, it's because it's explained here in the error message, because of short circuits. So if you use AND operator, and if this is false, in a normal programming language, this will not be executed. But with Noir, it will be executed. So to emphasize that it doesn't work as in a normal programming language, we don't support it. And instead, does it say what to do instead? Yeah. Instead, you should try the bitwise operator. Is there a question? No? Okay. Hello? I couldn't hear you. Okay. So we need to use bitwise operator. So in fact, it turned out that this is not so convenient. So the reason is because of the precedence of operators. The precedence of bitwise and logical operator is not the same. So finally, we came to the conclusion so that it's not a good idea to do that. But meanwhile, you have to do that, and I recommend to use parentheses just to make sure that precedence, you have no issue with precedences. Okay, so here also, and that I have one here. So of course, bitwise on a Boolean and logical on a Boolean should be exactly the same. So, except for the precedence. All right. So now, what is the error? Ah, yes. So here the error is not really clear, but it complains about this line, return false. So in fact, we don't support early return statement in Noir. So basically, you cannot do that. So the way so what should you do instead? So one possibility is to create intermediate variables and then add additional if statement with these intermediate variables. But that can be pretty confusing, I think. So here, what we want to do is to say that it doesn't work in that case. So there is an easy way to do that with Noir, is to use constraint statements. So you can see constraint like it's a bit like an assert. By the way, we'll probably rename it as assert. So it creates a gate in your circuit that makes sure that this expression is true. So this is exactly what we want to do. We want this to be true. So if this were not true, then you will not be able to generate a proof. The proof will fail, and we will even not try to generate the proof. We will say, oh, the constraints are not satisfied. So here, if it is 0, it's okay, and if it is not 0, so I want it to constraint to be 0, okay.
Should the first constrain, when you put the parentheses, you put the parentheses around aij, should it also include the less than 1?
So you see, so the parentheses are, so the parentheses are for the bitwise operator. I was explaining that because of the precedence, it's better to use them. And by the way, it should be like that.
Right, yeah.
Okay, that's what you were saying. Okay, thank you.
Yeah.
Yes, this is correct. So we don't need parentheses for the constraint. So I could put them, but it's not necessary. It will be fine. Oops. Okay. All right, so now I constrain this to be 0, and then I assign it to 1. Okay, so far so good. Here I have a return as well. So basically here what I want is, I want this. So if it is not 0, it should match. So what I can do is say either it's 0 or it is the same. Okay, do you all agree? Oh, yeah, I should probably return, you will complain. So I can return something at the end of a function. I just put my expression without semicolon, and it will be returned. For instance, if I don't do that, it will complain that I miss a return statement. Oops. Somewhere. Okay, I have too many errors before, so oops. Let me clear that. So let's solve the errors first. I cannot find solution. Why is that? So solution is here, so the error is not that. Did I? No, it seems okay. So let's see the second error now. He's telling me that he doesn't like this this symbol. I'm not. Okay, and this is because we don't support reference in Noir. So everything that you put inside the function is as argument will be by copy, by value argument. So it will be copied to inside the function. So this is not really a problem because like copy in the circuit, copy are very cheap. That's the first reason. The second reason, you will see it later, so that the compiler is optimized them anyway. So it will not create a copy if it doesn't need to. And the third thing is maybe if you will introduce reference later on in the future. The reason is because sometimes it's quite convenient to modify. You have a function that take your data, modify it. So you just want your data to be modified by the function. So this kind of expression of syntax, maybe we will add it in the future. But for now, we don't have it, so no reference. You can imagine everything is copied, but you don't care about really about the impact of the copy to the performance. Okay. Okay, so now he is complaining about usize. So indeed, we don't have this type usize. Again, in the future, we may add it. It makes sense to have it, but for now, we don't have it. So yeah, let's use a U32 instead, right? So we have like all integer types except usize. So you can have U1, U12, U15, whatever, up to a limit. So we don't support big integers. So the limit will be half of the size of the prime number that is used by the probing system. So for instance, with the Aztec probing system, the prime number is 254 bits, so you cannot go over half of this, so like 120 something for integer types. Okay. Okay, so now the error is what? Oh, I forgot to remove this, but another one? Oh, I'm sorry. Okay. So now he's complaining missing pub keyword on return time. So yeah, when you return from the main function, technically, this value, in fact, is an input to the circuit, and it's always a public input. So we want the user to be clear that this is public, so he has to write pub, just to show that it is public. Of course, if you want to hide the return value, you just don't return it, and that's it.
Okay. Is the return type of main always a Boolean?
No, you can return whatever you want. So for now, you can return integers, you can return arrays. We don't support structs as inputs and output of main, but this will be added, I think, very soon.
Cool, thanks.
Okay. Next error. So this is the biggest problem. So expected type comp time field, phone type U32. So what comp time means, so it's not a good name, but we don't have a better one for now. It means compile time, known at compile time. So basically, if you want to index an array, the compiler must know the value. Here, the value is coming from A, which is the solution. So it's coming from inputs of the circuit, so you cannot know the value. So it's complaining. So this is, I think, a limitation of Noir, an important limitation. Of course, we will support this in the future, but for now we don't have it. And we will, I think, have it like in a few months, but not next month. So we need to work around that. So yeah, does anyone has some ideas? So what to do? So we want here to check the line, that the line is correct. That is, we want to check that all the lines have number from 1 to 9. And we cannot do it like that. Okay. Yeah, it's not an easy exercise, no worries. So one solution, if you remember what I was showing with the cards, the verifier select a line, the prover takes the cards on the line, sort them from 1 to 9, and then give them to the verifier that is checking that it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, we can just do the same. So how can we do that? we just need, so we don't need this array because we cannot write to it like that. But what we can do is we can sort, we just need to sort this array. So AI. So here I'm using the standard library to sort it. And then I'm checking that it is equal to from 1 to 9. Okay. And we don't need that anymore, in fact. So, oh yes. So, so I want to constrain that this array sorted is equal to that. Okay, now it's better because I was trying to assign this value to something that is not a variable, so he was not really happy. Now it should be better. Ah, yes. I need to tell him that I want to use the standard library, so I can do it like that. Okay. Oh, yes. So it's complaining that G is an unused variable, which is the case. And in fact, yeah, I don't need it at all. Right, because now I'm sorting. So I will comment it for now. Ah, okay. So now you see the error. So yeah, it's not a very nice error. So here, in fact, it's the type system that has issue with generics. So let me show you the yeah. So this sort function was just added today, so it's normal. So this is the standard library, and this is the sort function to sort an array. It's using generic, but then the type system is not able to know the size of the array, so he complains that he's not able to compare them. So okay, it's okay. Let's just copy it and use it. So I will create my sort function. So this time I'm not using generic, but we use 32.9. Then I'm going from 1 to 9. Okay. Okay. Okay, only 2 errors now. But so yes, the famous, very famous error. So for some historical reasons, I will not explain them. We require a semicolon after a for loop. And by the way, I already put them. Yes, of course, because I copied from the standard library. So on every for loop, you need this semicolon. So maybe we will remove this, but maybe we'll keep it. It's not very important. There is some reason, but not very important. Okay. Okay. So now the error is saying arrays are not supported, which is a big problem because I'm using 2D arrays. But in fact, yeah. So we will probably support this in future. For now, we don't support it, and it's not a big problem because it's quite easy to emulate a 2D array with 1D array. So here, instead of having an array of array, I will just have one array of 81 elements. 81 elements. And then, like, instead of accessing my element like that, I just need to do 9 times I plus G. All right. So no big deal, in fact. So I still need this. Okay. Of course, this is not an array anymore, so I need to construct my my line. So let's start with a line with 0, and now write this equal to 9 times I plus G. Okay, so now I've created my line, and I can check that my line is correct. Okay. No, okay, so now it's telling me that my variable needs to be mutable, which is correct because I'm modifying it here. So let's just say it's mutable. Oops. Oh, I just see the second error here. I forgot again the semicolon on the for loops. And the last one is what? Ah, yes, okay. I forgot here. 9 times I plus G. Okay. Woohoo! Okay, so we could generate the circuit. Here you see the number of gates in the circuit, but then I was not able to prove in saying that the prover file is not properly formed, which is, of course, because here I'm using these 2D arrays and I don't have it anymore. So just let me copy the proper. Okay. So now I have just one big array. Oops. Solution equal. Okay. Okay, still have an error. So now he's telling me that he wanted three values, but he got 2 of them. So indeed, there are there are 2 values in here, the solution on the puzzle. But you remember I told you that the return value is in fact an input also to the circuit, so we need to provide it. The good news is that we don't need to compute it because it's computed when you prove it. So you can just put an empty value like that and it will work. You can see it by the way. So let's prove. Oh, I forgot to save my file. Okay. Okay, now it's generating the proof. Yoo-hoo! So we have the proof. And you see now we have this verifier toml file, which contains my return value, which is 1. So the verification is correct. And I have also the puzzle. Okay. Okay, so we managed to do it. That's very nice. One thing, no, okay. Yeah, maybe I can show you. Yeah, I will show this.
Can I ask a question on in the in the prover.toml file, why is the return type not specified? Like, why don't we set that to just like true in the input file?
Yeah, good question. So you can, for instance, if I put 1 here, it will work the same.
So like if we left it as like the quotes, if the main returned false or something, it also would have generated a proof, right?
So you see, I generated the proof. Now I put 0. I guess it will answer your question. And now with 0 is not happy.
Oh, great, cool, very cool.
So because you don't need to specify it because it's computed when you generate the proof, the value is computed because it's a proof of execution. So we need to execute the program. So we know the value because we execute the program. Okay, so what I wanted to show is this is the number of gates, so 13,000, and we are going to experiment to see how we can reduce this number. So check, we'll call it like set or check card.
Can I actually ask one more question? So you said,
Yeah, please.
sure, it's using the Aztec proof system. What proof system is used in Aztec under the hood?
So it's a turbo Plonk.
Okay, cool.
That's why we have custom gates. So I want to experiment with several ways to check this. And I will do just one that is using sort. Okay. So you see that I'm calling several functions. Every call is by value, so I'm copying the array several times. But at the end, it doesn't really matter. Oops. What did I do? 9. Oh, it's A. Okay. So you see the number of gates is exactly the same. So the compiler was able to optimize this this copy. So really, you should try to write clean code. Don't try to optimize stuff that the compiler is optimizing. Another example, so like I show you before we do real optimization, is like, again, don't try to beat the compiler. So here, another way to express this, for instance, I could use like, for instance, an if statement. So if this is not 0, I must have this constraint. Okay. Number of gates exactly the same. I suppose it was the same one, right? Let me just check it. Yeah, it was the same. So really use the way that you prefer. to write it. That is makes more sense for you. And another example, so the two are exactly equivalent. Like somebody smart say, okay, maybe I can remove this or, and I can do something like that. If I multiply the puzzle by the solution, oh, wait. If we do that, I don't need the OR statement, because if it is 0, then this will be 0 and this will be 0. And if it is not 0, it should be equal to this. So this times this will be equal to this times this. So, oh. So I could remove the OR statement. But if you, oops, what I've done again. Oops. Yeah. I have two loops on only one. Okay. So it works, but the gates are are greater now. And in fact, this is incorrect. So maybe will explain later on why it is incorrect, but it is incorrect. So don't try to beat the compiler. The compiler is here to help you, and he's doing a good job. That being said, it's possible to improve these checks here. So we want to check that this line has number from 1 to 9. So has somebody some idea of what we could try? Okay, so one possibility, for instance, if you remember at the beginning, we were trying to check that there were no duplicate number in the line. So what you should do is, what you should know is that, well, in fact, there are several ways to try to optimize this. So one is, of course, the sort algorithm. So this sort algorithm is, you can see it's a quadratic here. It's insertion sort, it's not very performant. But sorting in a circuit also is not easy. What I can tell you is that with when we will connect to the next version of the Aztec backend, which is ultra plonk, we will be able to do set equality, and with this we will be able to do, let's say, non-determinism sorting using set equality, and then we will be able to have a linear time sort done by the backend. So I think doing sort is the best thing here in that case, but with a proper sort implemented by the backend, which we don't have for now. Okay. So this sort is quadratic and also is doing a lot of comparison. So you should know that, like in a circuit, arithmetic operations are very cheap, and non-arithmetic operations are expensive because they need to be emulated with arithmetic operation. So here, comparison is not arithmetic, so this is a bit expensive. So we should try to remove them. And but then it's not easy to sort without comparison, right? So if you remember the Rust version where we were checking if there was no duplicate. So this can be done. Let me write a function here. No duplicate. So the idea is that if you have a set of elements, let me just write the ID here. I have my elements that, and I know that there is no duplicate in this set, and I want to add an element. No, add not in the sense like in the sense add to the set. So union. I want to add, and for the resulting set to still have no duplicate, then that means that A is distinct to all elements of S, right? This one will be, if this one has no duplicate, then this one has no duplicate only if I have this, okay? And this is quite easy to check. So how do I, I can just loop over all elements of S and check that they are distinct. So let's do that. So I should, I will take all elements for G in 0, 9. Oops. Oops. K in 0, J. I want that the element J is distinct to all the previous one. Okay. So if I do that, that means that in this array there is no duplicate. And I did my semicolon. All right, do you agree? And the good news here is that I have no comparison, like inferior, superior. So if I add this constraint, so like now it's just one line, so tac, tac. So my elements are from 1 to 9 and there is no duplicate. This proves that the elements of the array are exactly 1 to 9. Okay? So now let's try this. So this function is doing the same as this one, but you can see that they are really different. So like it's not a compiler optimization, clearly. The compiler could not have come with this. So let's try this.
I think the constraint should be within the for loop, right?
Yes, so you are right. This will work. Well, this will compile. This will evaluate
no, I mean the constraint on line 27, because we haven't defined like I, right?
Thank you. So it should be a G.
Okay, yeah.
And also here I need a constraint. That's what I wanted to say. Yeah. Because if I don't put a constraint, it will just evaluate to a Boolean, which will be true or false, but then it's not failing the circuit, having a Boolean. Okay. Now it's better. Thank you very much. So what I'm saying is this function is doing exactly the same as this one. At least the purpose of it is the same. Like the content, of course, is not the same. So remember, we have this number of gates, and now it was 30,000. Okay, now we have much less, but it doesn't work. Interesting. So here we can see that this is quite annoying because we don't know which constraint is failing. So this is something that we want to add also to Noir, so to indicate where it is failing. So yeah.
I think it's in the constraint on line 29. We're constraining that it's less than 1 or greater than that. We should be checking that it's like greater than 0 and less than.
Exactly. Thank you. And it should be that now. Okay, this is what we want. Okay, so it's working, and you can see that we have much less constraint now. So cool. This is because we avoid all the comparisons, because this is still quadratic. So we still have comparison, by the way, so we will see how to remove them. But before that, yeah, I want to show you the most important optimization that you can do. So this is the first thing that you should look at is the types that you are using. So we have mainly integer types for now in Noir. The most efficient type is the field type, so that corresponds to the native field of the proving system. So this is, if you can use it, it's the most efficient. If you don't know what is a field, maybe you should not use it. And then the second, what is interesting also is to try to limit the most possible the range of your integers. So here we know that our number should all be between 1 and 9. So in fact, using U32 for this is not good, because U32 allows for very big integers, but we don't need that range. So like, if I ask you what range what number of bits I should allow for my integer, you know? Yeah, it will be simply like a U4, like it's an hexadecimal, so 16. Because with 0 to 15, I can represent my numbers for the sudoku from 1 to 9 without any issue. So I should replace all of them with U4. And now let's see.
Does it support like U of any number or like powers of 2?
Yeah, that's what I was saying at the beginning. So yeah, any number. So you can have U1, U3, U78, whatever, until a limit, and this limit depends on the characteristic of the field that you are using, that the proving system is using. Sorry, so for Aztec backend, it's the prime is this number of bits, and you will be able to use U with half of this number of bits. So half of it is like 1 to 8, no, 1 to 5, and probably 1 to 4. Like, this will be the maximum that you can use in Noir with Aztec proving system. Okay, so you have seen that the number of gates have reduced a lot. That's pretty massive. So let's see if we can do better. So we see that we still have some comparison here. So my question is now is, can we remove this comparison? And if yes, how?
You can check that it's equal to 1 or 2 or 3 or 4 or 5 to all the way to 9.
Yes, I'm not sure it will be better, but yeah, we could try that. So what we want is 1 or, put a parenthesis, 2, 3, 4, 5. Oops.
Or maybe there's a way to take advantage of the fact that like it's only U4 now.
Yes, so let's try just for. So you see 6,000, it's more in fact. But yeah, it's a good idea to try something. So this is not good. So what we can do is that take advantage that we know that they are all distinct. And we have a bunch of distinct numbers that are positive. Okay, and we want that this number are 1 to 9. So when in this check, in fact, is to sum them and check that their sum is 45, which is the sum from 1 to 9. So here. Okay. So now we don't have the comparison. Oh, yes, it must be mutable. Sorry. But it doesn't work. So do you know why? Do you have an idea? It's a bit tricky. So the reason is, yeah.
So is 45 not in U4?
Exactly. Yes. Good point. So because of this, we have not given a type to S, and because of this line, the type system has okay. In fact, what you want is a U4. So S is a U4 now, and when you do that, you are checking a U4 against 45, which it will never work, of course. So, but of course, we must not take. We should not do that. Like this is not good because then I just need to have like a multiple of 16 in my sum and it will work. So what we really want to do is this, constrain S to be 45, but that means S must not be a U4. So we should use something else. And I was, if you remember, I was saying that the most efficient one is a field. So let's use a field for S. Of course, now the type system will complain here, but it's not a problem. We can convert this to a field. So a field is a very big integer, like 254 bits. So it can fit a U4 with a tissue. So this is like this is just saying the compiler don't care about consider this value as a field. So it's not creating any specific constraint.
Would it be more efficient to put S as like a U6?
I don't think so. Let's see. So we have this number of constraints, 2481. So let's try what? 5 will be 32, so U6. The problem is that also like if we have, okay, let's do that for now. And then I will tell you why it's not a good idea.
We also need to update.
Oops, yeah.
Yeah.
Thank you. So it was 24 something. So you see it's bigger. So the most efficient one is the field. And this one was not a good idea because like the number in A, like imagine for instance that A is 9999. So it cannot be because we know they are all distinct. But if it is like, if it is this, something like that, it's possible to overflow the U6. And maybe it's possible to get 45 with number which sum is not 45. You see what I mean?
Yeah. Yeah. Okay.
I don't know if it is the case, but it's dangerous to do that. So with field, it's fine. You are not going to overflow field by adding 9 U4. This is for sure. So okay.
Why is it more efficient actually to use like why does it lead to less gates?
Yeah, it's a good question. So in fact, so we compile down to a circuit, and a circuit is a bunch of constraints living in the field. So like every variable we have, we need to represent it with a field when we compile to a circuit. So if we have directly a field, then we don't need to do this conversion. So it's the best thing that you can do.
I see. So it's one, I guess, for the question, like if we replaced like all the elements of A right now are U4. If we replaced all the elements of A to be field, would that be faster?
No, because then you have other problems. Because
of like overflow stuff?
yes, exactly. So like if you sum a bunch of fields and you check this, like it could be -1 plus
Right.
36 plus 0 or whatever.
Right. So maybe it's not sound, but would the circuit have fewer gates?
Yes.
Okay. Okay, that makes sense.
All right. So there is a last optimizations I wanted to show you. So this one is is a bit, yeah. So it's inspired by some check protocol. So some check protocol are old protocol that that allows to prove the summation of evaluation of a polynomial over an hypercube. And it's an old protocol, but it's going to be used in all the next generation of proving system. Like, for instance, Hyperplonk is using it. So we are not going to use some check here, but just we are going to sum a polynomial. So that's why I say it's inspired by some check. So let's do another last one. So I still have my line. Yeah. So let me explain you the idea. So I want to check that the numbers are 1 to 9 in the array. And I'm considering the polynomial. Well, first, my array, it's a bunch of number, I1, A2, etc., till A9, okay? And I consider this polynomial, which is x minus A1 times x minus A2 times, etc., x minus A9. All right. So now, if this set, so not as an array now, but as a set is equal to 1 to 9. So when I say as a set, that means without any ordering. Then what can you say about of P of 1? So if this array has 1 to 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 as numbers, then that means one of them will be 1. So when I evaluate P of 1 of them will do 1 minus 1. So it will be 0. Okay. Then what about P of 2? So again, if 2 is inside the array, one of them will be 2, for instance, this one. So if I compute P of 2, I will do 2 minus 2, so it will be 0 again. And etc. All this will be 0. So then what does that mean if I sum them? So A equal, let's say A as a set equal this, that means that the sum of P of 1 plus P of 2 plus, oops, P of 9 equals 0. All right. Then what about the reverse? If I have this sum equal to 0, does that mean that A equal is this set? So the answer is no, but it's not likely to be something else. So then the question is how likely it is. So I wrote a little program. To try all the combination, because we know that the elements are U4, so it's from 0 to 15. And then I evaluate this polynomial and computed this sum. And these are the polynomials, so they are sorted, of course, because any permutation will be the same. All the polynomials that evaluate 1 to 9 is equal to 0. Okay, of course, I did not put the one that we want. Which is 1, 2, 3, 4, 5, 6, 7, 8, 9. And for instance, if you see the first one, the sum of its coefficient is exactly 45. So we cannot use this trick here. So, but what do we see here? That all of these, they contain 10. So what does that mean? Is that if I have this equals 0, that means A is one of them, or this one. Okay. So if I have this and all my AI not equal to 10, then that means my set is like that. Okay.
That's nice. So you could also do it by like introducing instead of adding up the P1, P2, P9, you could like add randomness, right? When you combine them. But
Yes.
I'm guessing it doesn't support, Noir doesn't support like drawing random values.
Yes. So like having random values in a circuit is very difficult.
Right.
So it's something that we are considering. The idea will be to hash all your witnesses and use this as a random oracle.
Right.
But for now, we don't have it, at least.
Right. Yeah, that sounds like an interesting idea.
Yeah.
Cool.
So we need to do without. So that's why I came to this. So now it's quite easy. We just need to check that they are different to 10. So and we need to evaluate the polynomial. So let me just, I don't want to. I don't have much time, so I will just write it directly. So this is the best solution I could come with. So what we are doing here. So here I am evaluating my polynomial from 1 to 9. Okay. And I start with, because it's a multiplication, so I need to do 9 multiplication. So I start with 1, and then I multiply with k minus ai. So like I'm doing this, times this. Oops. Okay. I need to use a field, as you remember, because if I use U4, it will not work at all. Okay. And then this computes P of 1, P of 2, etc. for each K, and then I sum them. Okay. So then what I've computed here into S is this. So at the end, I will check that this must be 0. That's my first condition. And then the second condition is this. So I've not done that. I can show you if we have time, and if you want, because it's not that interesting. So instead, I've noticed that, okay, they all have 10, but they also all have 0. So first thing is that comparing to 0 is a bit more efficient than comparing to 10. And not only they all have 0, but they all have 2 0 inside. Okay. So what I need to do now is I need to take 8 number in my line and check that none of them is 0. Okay. And so that's why it's from 0 to 8 now. And how do I check that 8 of these numbers are not 0? I just multiply them together. And then if they are all non-zero, the result will not be 0. And if one of them is 0, then the whole product will be 0. Okay. So this is more efficient at checking that each number is not 0. So this would be my best solution. Let's try it. I don't remember the number that was before, but it was 2000 or something. So now it's 1500. I did also the full solution with also the line, the square, and the columns. And as a result, I have less than 3000 gates for a full Sudoku solution, which I think it's not so bad. So, like, yeah, if you have some question, if you want, I can show you why this is better than just comparing the numbers, but as you want. So, like, I would prefer to answer questions, maybe.
Awesome. Thanks. So, are there, so like this was awesome, like the transformation starting from like a Rust program and then like trying to compile it and fixing errors to get to the Noir specific stuff. Is there like documentation on like on translating, general guidance on translating Rust programs to Noir?
No.
Not yet. Okay.
No. Unfortunately. Yes, so I know that some of the errors, sometimes they are well explained, but sometimes it can be a bit difficult to understand what is going wrong.
Yeah. And are while loops supported or no?
No. For now, we only have this for loop with constant range.
Oh, right. Okay. Cool.
What we do have, which can be nice. Let me show you. Like for instance, here. No, not here. Here. What I could have done. Not A, but call it G. In A, you can do something like that. G, sorry. Like a for each.
Got it. Yeah. And that should be the same number of gates.
Yes. Just a sugar syntax.
Cool. Yeah. Nice. Okay. Anyone else have any questions on the call? Okay, well, oh, Maxime, do you have a question?
No, I was just gonna say thank you. I'm all.
Yeah, thank you so much. This was such an awesome talk and demo. How did you guys like how did you build this? Like did you build everything from scratch, or did it go from like, did you fork Rust or something and then like alter the Rust stuff, or what was the approach?
No, it was mostly from scratch.
Awesome. Yeah, this is really, really cool. I really like the syntax, and it's very easy to write a program now. So awesome. And like also your presentation was also really, really cool. Like the thought process of like fixing all the errors and showing and explaining all the functionality was really, I thought, effective. So yeah, thanks a lot for
Thank
preparing
you.
and, taking the time on a Friday to teach us. So yeah, thanks so much. Thanks so much. I think we'll end it there. So yeah, thank you.
Okay, thank you.
All right. All right. Take care, everybody, and enjoy the rest of
See ya.
your Friday.
Yeah,
See ya.
good. Have a good weekend. Bye.